Even the most talented chess grandmasters pale in comparison to mysterious machine learning algorithms. But how do they learn and predict moves with such stunning accuracy? Today, I'm setting out to find out how these models are made, and I'll have a few things to share with you along the way. The very first step in any data science problem is gathering and exploring the data, as we all know. So thankfully, in today's day and age, it's extremely easy. I'll be linking this in the description if you want to check it out. This data set, let's say you work for a bank and you want to know when people are applying for loans, are they going to be good customers or are they going to be bad customers and not pay their loans back? That's what you're trying to figure out. And in order to figure that out, you're going to use all the different data that you've collected. So here it gives us a description. We're not going to read that, it's kind of long. And it tells us all of the different data that we have to be able to find out, are they going to default on their loan or are they going to pay back their loan? And about 20% of these naughty people did not pay back their loan. We can't have that. We're going to do a better job next time of determining whether they'll pay it or not. So based off of all this information, loan request, mortgage due, all these different columns of data, we can make predictions about whether a customer will or will not default on their loan. The next important step in this process is actually taking care and cleaning up the data. So there's a lot of different ways that this can happen. But here I have imported the data in SAS, and you might want to take a little bit of an exploration of it, which we can do. So some software will allow you to just run the results of a data exploration. So this will show us some trends and some summarizing information of the data. We've got like 6,000 observations, that's quite a lot. And some other important data that can be shown here. For example, the 20% of people who actually did not pay back that loan, and lots of other statistical information about each variable. Next, we are faced with the problem of cleaning the data. So a couple major challenges that are experienced by any data scientist when trying to make an effective model are missing values and too many variables to make an efficient deployment. So the first of these problems with imputation we can take care of. Imputing data replaces the missing values with a selected statistic value that would make sense for the given set of data. So if you have a bunch of people didn't answer if they were married for some reason, you could have the program go in and put statistical values there that make sense, and if they were or weren't married, which can actually make your predictions more effective. Another extremely important idea that can be used when approaching problems where there may just be too many different columns of data is feature machine and feature extraction. What these strategies do is they apply different statistical techniques like principal component analysis, or PCA, to basically simplify the complexity in high-dimensional data retaining trends and patterns. Essentially, you get lots of columns, you start with lots of columns, and then it reduces the amount of columns by combining the values in multiple columns into one single value that still holds much of the important information that the previous multiple fields held. This is important for multiple reasons, but one of the main benefits is it increases the efficiency of your model. Now, moving on to the different models used. I won't be making explanations of every single one of these models, but we've got a logistic regression model, a decision tree, a random forest, a gradient boosting model, a neural network, and another decision tree that has no data cleaning ahead of it. And then finally, we used an open source node containing a gradient boosting Python model. And we can compare all these models quickly through SAS. So many of these models I was able to create just using SAS's pre-programmed routes, but some parameters have been tweaked. Looking at these results, we do have a clear winner. Gradient boosting with feature extraction and feature machine was the clear winner out of all of these different models with a whopping 92% accuracy. This is huge, and it means that we can predict with much more accuracy than before who would or would not pay back their loans, saving us some money, which is what this is all about. So this is a huge win. In second place, we have the random forest. And you may notice that there's a couple of different values that are important here. There's a lot of other different statistical values that you probably would only understand if you have a higher degree in statistics. But an important one here is area under ROC. Area under curve is an important statistical relationship. It shows the ratio of true positives to the complement of false positives. So basically what this is saying is the higher this area under the curve is, the closer to 1, the better the model is at distinguishing between the positive and negative classes. And depending on what you're predicting, limiting false positives can be either vitally important or just pretty good. In this case, though, having a high area under the curve is pretty nice. And while we're talking about that, let's take a look at who did this best. And we'll see that our open source node actually performed extremely well in differentiating between the true and false positives. It also had a reasonably high accuracy, so the open source gradient boosting model with no data preparation actually did quite a good job. So since we had a couple winners in that competition there between the models, I thought I might explain a couple of the most successful models that we used. They were gradient boosting at number 1 and random forest at number 2. And actually, we had decision tree models in that pipeline as well. And the funny thing is, both gradient boosting and random forest are actually, well, random forest you might be able to guess, but they're both created from decision trees. So decision trees you can see here, basically you start with a case and there's, maybe a probability for whichever choice is chosen. Decision trees are extremely popular in data science and just computer science in general, and great ways to model, well, decision making. Gradient boosting is actually a sequential series of decision trees that the model is ran through, while random forests instead are multiple decision trees that are trained on different samples of data within the set. I genuinely hope that this overview has provided you some somewhat valuable insight on how data scientists tackle statistical problems. I know I've learned a lot. Stick around to see more data science content, especially coming very soon is an explanation of one of the simplest machine learning models, linear regression, and we'll get into exactly how that works. Thank you so much for watching. Have a great weekend.